Okay, thank you. So good morning, everyone. My name is Sofia Pelizzoni. I'm a third-year PhD student at the University of Padova, and today we'll present a study conducted with Professor Mauro Ricotta and Giovanni Meneghetti entitled Correlation between Intrinsic Dissipation and Uniaxial Fatigue Strength at the two load ratios in 42 chromolybdenium-4 quench and temper steel for marine applications. Okay. In the first experimental observations, list that a material undergoing a fatigue test is subjected to an increase of the surface temperature, which is seen to rapidly increase at the beginning of the test, and then it tends to a stationary value. The higher the applied stress amplitude, the higher the level of stationary temperature reached from the beginning of the test. According to the thermographic technique proposed by La Rosa and Visitano, the material fatigue limit can be determined by extrapolating down to zero the best fitting curve correlating the stress amplitudes and the stationary temperature increments. The benefit is that since it is unnecessary to run the fatigue tests up to failure in order to achieve the stationary thermal rise, the thermographic technique was presented as a rapid tool able to estimate the fatigue limit. In spite of this, the temperature cannot be seen as a promising fatigue indicator, since it cannot be extended to geometries and test conditions different from the reference ones. An example is shown here with a plane and a notched specimen at the same material undergoing a fatigue test with the same load ratio. Even if the fatigue lives of the plane and bluntly notched specimens are approximately the same, the temperatures at the critical points here indicated are different. In general, because temperature distribution will depend on the local stress amplitude, test frequency, specimen geometries, and all the other boundary conditions that define the heat transfer rate from the material to the surroundings. Differently, if we consider the amount of energy dissipated in a unit volume of material per cycle, it is a more promising parameter for fatigue strength analysis of engineering materials because it is resulted to be dependent on the load ratio and applied stress amplitude, as can be seen from the synthesis here obtained on fatigue tests with AISI 304 steel performed adopting plain bluntly notched, severely notched geometries, so very different geometries, different frequencies, and also different boundary conditions. From the first principle of thermodynamics, the input plastic energy density, which is equal to the hysteresis loop area of material undergoing a fatigue test, is divided into a heat component, and that material exchanges with the environment, and a part stored as internal energy. By rewriting the equations, in terms of power and making the latter term explicit, a contribution linked to the temperature variation over time and another linked to the rate of accumulation of damaging energy come up. Under stabilized conditions, so here reported, the temperature variations, under stabilized temperature conditions, over time, sorry, I got a problem with the mouse. Okay, under stabilized temperature condition, the temperature variations over time is zero, and the amount of heat that the volume exchanges with the environment is constant. So a sudden interruption of the test leads to the plastic deformation energy density and the rate of accumulation of damaging energy drop. Since the heat exchange is the same a second before and a second after the interruption of the test, it can be evaluated by experimentally measuring the cooling rate of material from the test interruption time. The tests here were carried out on plain specimens extracted from a marine connecting rod, considerably large, as you can see here from these pictures. Tests were conducted under force control at 3 different load ratios, namely -1, 0.3, and 0.5, with testing frequencies ranging between 25 and 80 Hz. Almost all tests were monitored using an extensometer to acquire the material's hysteresis loops. The surface temperature was instead monitored by means of a thermocouple T-type glued on the center of the specimen parallel length. Temperature data were acquired using an Agilent device with sampling frequencies up to 22 Hz. Two testing machines were employed, a servo-hydraulic testing machine with a load capacity of 15 kN and an electrodynamic machine to enable the testing of higher frequencies. The fatigue tests are here plotted in terms of nominal stress amplitude versus number of cycles to failure. In particular, the hollow markers here represent the results of strain control tests at the load ratio equal to -1, plotted in terms of a stabilized stress amplitude. Instead, the solid markers correspond to the force control tests. Specifically, the series at R-1 is plotted in blue, the series at 0.3 is orange, and the gray one is the series at 0.5. In the latter case, all specimens reached the runout condition, so none of them failed during the tests. Thus, let us consider now the scattering fatigue life of the R-1 and R-0.3 series, which in the first case resulted equal to about 13, and in the second case it resulted about 32. In the following discussion, we will focus on a couple of experimental results. The first pair, which is here reported, one specimen was subjected under strain control and the other one under stress controlled at approximately the same stress amplitude. Then another couple is here considered, tested at a lower load level. In both cases, despite the same applied stress amplitude, the fatigue lives recorded were significantly different. It clearly emerges, as already highlighted in the literature, that when the results are plotted in terms of applied stress amplitude, the influence of mean stress becomes evident. The higher the applied stress amplitude, the higher the applied mean stress, the higher this influences also in the fatigue behavior of the material. Now, a quick comment on the same results plotted in terms of maximum applied stress. In the case of a load ratio equal to 0.3, here reported even more for 0.5, the fatigue life is limited to a minimum value of about 60,000 cycles, since the maximum applied stress corresponding to that life approached the ultimate tensile stress of the material. Now, by comparing the cyclic behavior of the material for the two specimens tested under high load in stress and strain control conditions, it can be observed that the hysteresis loops obtained from the stress-controlled test exhibit a progressive accumulation of a plastic strain, thus revealing a ratcheting behavior. The hysteresis loop at the 50th cycle, which is the yellow one here highlighted, then reaches the stabilized hysteresis loop, which is plotted here in blue color. Conversely, when observing the twin specimen tested under strain control condition, the hysteresis loops progressively decrease in their stress values, thus exhibiting a softening behavior. What clearly stands out, however, is the marked difference between the areas enclosed by the hysteresis loops, since the mechanical energy supplied by the material here is reported with a higher area submitted by the hysteresis loop, while in this case it is much lower. Particular here, the higher the mechanical energy supplied by the material, the shorter the fatigue life, and also vice versa. This highlights that the dissipated mechanical energy parameter is already capable of capturing the difference between the two specimens. Concerning the influence of mean stresses, the stabilized blue hysteresis loop here reported is shown for a stress control test. When the load ratio is increased to 0.3, the material exhibits ratcheting here until stabilization is reached. The stabilized hysteresis loops for the two load ratios are also here reported. Okay. Also here, the mechanical energy parameter calculated as the area of the hysteresis loops seems capable of taking into account the slight difference and properly correlate the fatigue life. So since for a higher value of mechanical energy, also the shorter fatigue life is here confirmed. At the 0.3, the material behavior is almost linear elastic. During the fatigue tests, the hysteresis loops were monitored for almost all specimens. The horizontal axis reports the number of cycles normalized with respect to the total fatigue life, while the vertical axis shows the dissipated mechanical energy density. Strain and stress control tests at R-1 are here plotted above, while stress control tests at 0.3 are also plotted here below. The dissipated mechanical energy density appears with flat trends throughout the entire fatigue tests in all cases. And by assuming the value evaluated at half fatigue life of life, it was assumed as a representative value. So the results were plotted in a double logarithmic diagram as a function of the total fatigue life. Here represented. Results show that according to the definition to Ellen, which requires to the calculation of the internal area of the hysteresis loop, it neglects the elastic contributes. Here it can be observed that fatigue life correlates within a single energy band for different investigated load ratios, so R-1 and R0.3. Covering fatigue lives between 1,000 and 1 million cycles. The scatter of this band in terms of fatigue is 10 here, which is comparable to the scatter of individual series plotted in the Wheeler curves. This confirms that the mechanical energy is an excellent indicator for fatigue behavior. The specimen tested at R-1, both under strain and stress control, correctly fall within the band, indicating that the energy parameter accounts for the different dissipation mechanism occurring in the two cases. Consequently, the effect of the mean stress disappears and a single energy-based curve is obtained regardless of the applied mean stress. So now let's move instead to the energy density released as heat by the material in the form of heat. Here we can see a temperature monitor test of a specimen that reached the runout at 2 million cycles and R-1 load ratio. Since during the test the temperature was measured on the material and it was regularly monitored, several interruptions were performed in order to measure the cooling rate of the material. An example is reported here on the right. Once the stabilization is reached, according to the theoretical model presented before, the test is suddenly interrupted and the cooling rate is measured at a sampling frequency of 22 Hz. The slope was evaluated over a time window of a couple of seconds and a temperature drop of about half degree, which is absolutely detectable by a thermocouple whose sensitivity is on the order of even less. By plotting for each specimen the measured values of dissipated heat throughout the test, we observe near again a constant trend. As before, the reference values were taken at half fatigue lives, and consequently, the dissipated heat was also assumed as a fatigue damage indicator. Also, in this case, a single fatigue curve is obtained, correlating the data independently on the applied mean stress. It is worth noting that the scattering life is slightly slower than the one from the mechanical energy curve. The two pairs of experimental data tested at 474 and 380 megapascal are also indicated, and they align quite well in terms of dissipated energy. For the specimen tested at 380 megapascal, Bicker's and Nico hardness measurements were also performed, revealing higher hardness in the specimen with the longer fatigue life. From the analysis carried out so far, so it appears that the material does not exhibit a mean stress effect when the experimental results are plotted in terms of energy-based quantity. Elena argued that the mechanical energy of the hysteresis loop should be corrected for the mean stress by accounting for the linear elastic contribution of the tensile branch, while neglecting the compressive one, which is non-damaging. In previous studies carried out on ISE steel and the C45 carbon steel, the dissipated heat exhibited differences when plotting the fatigue data obtained at a different load ratio. To account for the mean stress, so as a consequence, in 2016, a parameter was proposed that also included the thermoelastic contribution of temperature in order to compact the energy curves into a single scatter band. So why does not the 42 chromolybdenum 4 require such a correction? By comparing the curves obtained from the mechanical energy with the obtained from the heat, it can be observed that they are essentially in parallel one to each other for all the investigated fatigue lives, and with a constant conversion ratio of 0.88. This conversion ratio has previously been found to be dependent on the load ratio for C45 steel, which showed 0.9 for R-1 and 0.85 for low stress amplitude and lower for high stress amplitude. In contrast, for the present material, no differences have been observed between the load ratios -1 and 0.3. This conversion ratio thus uniformly translates the mechanical energy into heat, but further investigation are still required of this. So I conclude this presentation saying that the stress control fatigue tests have been performed on plain specimen extracted from a 42 chromolybdenum 4 quenchable temper steel connected bead rod under different load ratio. The classical stress life curves were obtained as expected. They were dependent on the applied stress ratio. The fatigue life were reanalyzed in terms of strain energy density dissipated in a single fatigue curve independently of the mean stress. The fatigue data were reanalyzed in terms of dissipated heat in a single fatigue curve independently from the mean stress. As a future work, we will go more in deep for the analysis of the influence of load ratio in the mechanical energy conversion from the current material and the materials investigated in previous analysis, which are C44 carbon steel and NIEC 304 steel. So I thank you for your attention.